velocity, and we saw that there's still a velocity up and down of the fluid through that surface.
So we're assuming the bottom of the object is the surface of the wave?
No, we're assuming that this geometry is within the wave field, but the pressure that's applied to it is the same as the pressure that would be there if the float was not wave.
Okay.
Right, so we've actually got a wave that's like flat, and say we go beneath the wave crest, right, and we're just taking all of the points on the surface of the float, right, and evaluating pressure. But the float itself is not actually changing the wave field. Right, because if we have a solid float there, then really we should have the velocity across along this line is exactly the same as the velocity of fluid particles, but we're allowing the wave to still generate and pass through the float. So it's like having a very porous float. Right? So treat the float as a number of dots that don't apply any resistance to the float, right, instead of a solid surface. So of course, if you write it in a verbal sense, see, that's fine. You can write FFK is equal to the integral of pressure times the surface area, where pressure is given by this. And this is the pressure field without the device in place. Right? So that's the first part. Ferrocril force. Force on stationary immersed geometry due to the pressure field that exists without the geometry in place. So consider your float like that as a set of points in a wave field rather than something that applies resistance to the wave field. That make sense?
Yep.
Okay. So that's Ferrocril then. And in that case we can have flow. Let's have flow as volume then. Flow can go through this surface. So flow can come up on this side and down on this side. Right, so flow can go backwards and forwards through that surface, and it can still move across through here, across under here. Right, so that, if you continue then that line of thought, that starts to define another component of force that we're interested in. So what then is the scattered wave force? Which is only briefly described in the notes. Right, so particles can do this at the moment. They can go up through the surface of the float at this point, down through the surface of the float at that point. Right, so if we don't want that to happen, which obviously we don't, then there's going to be a change in the pressure field in the wave. So if we say, well actually, let's consider another wave field that would exist to cancel out that velocity, and that velocity, and that velocity, and that velocity at these points, right? Then the pressure field that exists due to cancelling out those velocities is your scattered wave field. Right? So we're then going to apply another wave field that cancels that back out. So we've got none. Cancels that back out. So we've got none. Right? We don't mind about that one as long as that's zero. And that one can still occur because it's in the fluid. But by changing those, we're going to change that one. Right? So the Ferrocril field assumes that your float is completely porous and flow can go through it. Your scattered field is the force that you have to apply back to the field to make the float solid. That's making the solid surface of the float. Right? And then, as a result, this surface no longer exists through the float. We've then got this boundary condition like this. Right? So now our float has got a rigid boundary within the fluid domain. To make these white components of velocity cancel out the blue components, we're going to have to slightly change this wave field. So this surface elevation changes from something like this perfect sinusoid to a sinusoid with a change of amplitude as we move away, and then it returns to the right shape long term. But that doesn't matter. So it changes the wave field very slightly. Right? Something like that. So our surface elevation changes slightly because we're cancelling out the velocity components that are going through our porous float. So that's Ferrocril and scattered. Ferrocril is that. We don't need equations for scattered because we haven't really covered them. It's sufficient to say that it's the pressure field that exists to cancel the velocity across the surface of the float. Right, so in each of those cases, what's the float doing? We've got velocities here where the wave field itself is generating or producing a particle velocity that can go through the float. We've created another wave field to cancel that out. Right? Well, what's the actual boundary doing? So if we were to sketch this float now then as a solid body, right? Is that float moving in each of those cases?
No.
Right, so Ferrocril and scattered, the float is staying perfectly stationary. So we could write that the velocity of the float, if we take its fixed point at the top, say, it has a velocity vector u of the float is exactly equal to 0. Right, so the boundary is stationary. So all we're doing with this scattered wave field, the white arrow, is doing minus the velocity of the wave field in the presence of the float. So that gives us forcing on a fixed structure, which oil and gas industry like. Right, so then radiation force. What's the radiation force? Quite the opposite, obviously. It's the only other thing we've got, I think. Radiation force. Right. Radiated wave force is then just changing this part. So instead of having u is equal to 0, we've then got the reverse term of u is equal to a constant amplitude. Right? So in the second case, we've then got our float again, broken board, and now u is not equal to 0. Right? So radiated, scattered. So obviously not going to take too many hours over this. Question?
Hi.
Don't hear any dripping noises. Right, so radiated float is moving with an imposed velocity, such that it has a sinusoidal velocity. So by moving, what does it do? If we move it, so it's in still water initially. Right, that's our scale on water. So as it moves up and down, what does it do?
Makes a wave.
Creates a dispersion.
Creates a
Dispersion.
dispersion.
Displacement.
So it has dispersion, so just a wave, which happens to be a dispersive wave. That's fine. So if we move it down, to a lower position in the fluid, as you say, we're displacing some of this fluid here, right, and therefore increasing wave height here and making a crest initially, and then if we move it back up, it will come back to a trough. Right? So as we move it up and down, we move it down, we create a crest. As we move it back up, we create a trough as water comes back in underneath. Right? So, exactly, to move something in water, we require a force. So the radiation force, F rad N, is the force required to oscillate it with unit velocity. So that U is equal to the naught sine, let's say, over T. You know which way around we did it, as long as it's a cos or sine term. So with an amplitude of a velocity, a unit amplitude velocity. So then our radiation force is going to have a component that's imposed with this, and a second component that's imposed with acceleration. So we can normally write this as A, an added mass term, times 3, well, in mode 3 in this case, U dot plus U. Right? So to create this sinusoidal wave going in both directions, a radiated wave pattern in both directions, we require a force, part of which is in phase with the acceleration of the float, and part of which is in phase with the velocity of the float. Right? And that's it for that question, really. I mean, that's more than you need for that question because it's only about 5 marks. Isn't it? Pretty good. Right, so scattered and for our Krylov, both with a stationary float geometry, radiated float geometry of moving with an imposed velocity, and this is the force required to create that imposed velocity of unit amplitude. Right, so is that it for my question? So as I say, you need both of those in terms of equations, so that equation, and equations for pressure. No, let's put it down. You know what those are. So you.
So the equation for scattered waveforms then?
No.
Not really. We don't go into depth what the pressure field is because it's hard to solve. But all it would really be is the pressure field such that U across the boundary is equal to U of the instant wave. So no, pressure field action of this creates that you actually see on it.
So the main difference is that for the first two cases, the device doesn't move.
Yep.
And the third case is that we have a stationary, a static water, and the device is moving up and down and it's creating.
To create waves. So why do we want to create waves?
Energy.
Yeah.
What about it?
To make energy.
To make energy.
Yeah.
Okay, what does that energy do? What would we like
Drive
our
a turbine.
radiated wave here
Drive a
to do?
turbine.
If the wave's going, if there's an instant wave here going in that direction, we want the float to move to create a radiated wave such that this wave, down wave, is partly cancelled out.